Welcome back, everyone. I hope you had a nice break. Now it's time for our second keynote talk today by Joe Hellerstein, whose keynote topic would be Better Data Engineering Through Technology. Joe is a professor at University of California, Berkeley, and founder of the software company Trifecta. He works broadly in the field of computer science and data management, covering everything from data systems to human-computer interaction, and machine learning to networking. Over the past 2 decades, we have seen data become an increasingly important asset to nearly every organization. We have seen the evolution from big data to data science, and now to data engineering. The next step in sight is an open and inclusive data engineering cloud that brings together a diversity of stakeholders to transform businesses, science, and government organizations. This talk will show us what an inclusive data engineering cloud looks like and how a decade of innovation in computer science, from AI to interactive visualizations, from program synthesis to data operations, can enable transformational promises of data. Welcome, Joe.
Thanks for having me. It's good to be here. So thank you for that lovely introduction. Maybe we'll just jump right into the talk without further ado. Clearly, we're all here because we're excited about the technologies, the techniques, the mathematics behind data science. And conferences like this are a wonderful opportunity for us to get to know new technologies and to really dig in and kind of indulge our geeky interests in these technologies. But we can also ask the question, what has data science technology done for you lately? What has it done for us as professionals in the data fields? Okay, and that's one of the things that I really want to focus on today. So let me give you an economic perspective on what I'm talking about. And so I like to talk about this as the evolution or the contrast between rocket ships and washing machines, okay? So, you know, if you look back at the history of the 20th century, this is a photo of the Wright brothers, you know, who are often thought of as the founders of modern flight. They began the 20th century in Kitty Hawk, North Carolina, using gliders with no engines. That's where modern air travel and space flight began. And over the course of the 20th century, innovations in technology were incredible. It led to the invention of jets, of commercial airliners. We broke the sound barrier, and I understand that we'll soon have supersonic jets flying in the air again shortly. We did indeed build rocket ships and fly off into outer space, and we even built space shuttles that could go into space and come back. So a remarkable decade, the 20th century, in technology, leading us really to and through rocket science to rocket ships. And if you're, you know, a young person enthusiastic about technology, the idea of rocket ships is just incredible, very inspiring. My own personal interaction with rocket ships is a bit limited. This is a photo actually taken out my window at the University of California, Berkeley. And if you look closely, it is actually the space shuttle. It was flown on its last mission, so to speak, around certain parts of the country before it was retired. So this is as close as I've come to a personal benefit, if you will, or a personal interaction with rocket ships, okay? Which was pretty cool, but didn't really affect my life in any serious way. By contrast, look at productivity technology. So this is a photo, obviously, of women washing clothes at a public body of water. And, you know, traditionally, this is how we wash clothes. It was done at the side of the river with rocks and stones and abrasion of the clothing, right? And over the course of the 20th century, starting actually in the late 19th century, machines were invented to lighten the load of housework. And the thing that's really interesting is over the course of this century, of course, this photo is all women, and we're going to talk about that a little bit. Over the course of this century, this machinery, the household productivity technology, has become so good that we completely take it for granted. The idea that washing clothes is not a major activity in our lives is a gigantic change. And you can measure it in economics. So very interesting paper. It's called Engines of Liberation. It's appeared some years ago in the economics literature, studying the effects of 20th century household productivity technology on the workforce. Okay, and so what you see is over the course of the 20th century, the hours per week spent on housework dropped from something around 60 hours to something under 20. And the participation of women in the workforce went from about 10% to about 50%. Now, pay equity is still not there, but still, if you look at the effect of productivity technology, it freed up half the population approximately to enter the workforce. And so, in contrast to the space shuttle flying overhead, I can think about what my life would be like, or perhaps what my wife's life would be like, if we had to do our housework by hand. It's a remarkable change in the way everyone spends their day, or at least half the population spends its day. And it's a remarkable change in what we as a population can accomplish when we've unlocked the power of half the population to participate in other kinds of work than housework. Okay? And so when we think about rocket ships and we think about productivity technology, we might ask ourselves, which of these things is more important in the world of data analytics and machine learning? And I think we actually know what the answer is here. There's a lot of academic research that's the moral equivalent of rocket ships, whether it's new machine learning technologies or it's engines to process petabytes of data. For the most part, what's really missing in the space, and we're going to see this more in the economic slides coming up, is the productivity technology for data science. So when I think about where to invest research time, my time at the university, as well as where to think about starting innovative companies, I believe productivity is a place that we have neglected far too much. And in that spirit, I want to talk about the data engineering cloud and what that promises for the productivity of data science. Keep in mind that if you're a company that's using data science, your competitors have access to the same algorithms that you do. To a first approximation, the analytic and machine learning algorithms that everybody is using are coming out of open source. They're coming out of universities, or they're coming out of companies who's monetized, like the big internet companies. They're monetized more on consumer usage than they are on tech per se. So they're giving away, for the most part, we're giving away the modeling algorithms. So every company has access to the same algorithms. And thanks to the cloud, every company has the ability to access as large a data center as their workload requires, right? So everybody has access to the same computing power. The difference in competitive advantage, the difference in the efficiency of the organization you work for is the data that you actually have and the work that people do with that data to turn it into value. That's where companies will be differentiating, okay? Not on the core rocket ship technology, but rather on their ability to use it. So there's two key aspects from an economic perspective of this productivity technology. The first is to make efficient use of scarce labor. So for example, if data scientists are hard to hire, how can you get more people doing the work currently being done by your data science team? And the second is how to increase the labor pool. So there's simply more people who have the skills that are required. And simplicity technologies, productivity technologies, empower us in both of these cases. They make the people who are the scarce resources more efficient, and they allow people who otherwise wouldn't have been able to do this work to enter this labor pool and be able to do useful work in this space. And so I'm going to argue that technologies that simplify data science are good for everybody. They're good for the experts, and they're good for expanding the group of people that can do the work. And we hear this over and over and have been hearing it for a decade. So the first aspect of this, efficient use of scarce labor, DJ Patil, who's an advisor to Trifacta from the beginning, before he was the first US chief data scientist, had a book called Data Jiu-Jitsu, in which he wrote 80% of the work in any data project is in cleaning the data. Roll forward, it's 2018, we have the head of AI at Amazon AWS at reInvent saying the hardest part of AI is the data wrangling. This is not news, okay? But it hasn't been a big focus for a lot of people. And if you look at the talks that we're having at SDS, you can ask yourself proportionally how much of that stuff is addressing efficient use of technology. Big Data Borat perhaps said this best on Twitter. In data science, 80% of time spent prepare data, 20% of time spent complaining about need for prepared data, right? It's a bit of a caricature, a bit of a joke, but the point is much of our time is spent in the engineering process, not in the analytics. A more recent phenomenon, though, is that the labor pool is increasing. Data science is different now. This is a blog post by Vicky Boykis. Vicky is a very interesting blogger and writer who is a working data scientist here in the United States. And she had this very sort of interesting post where she observed that we actually have lots of data scientists all of a sudden. And I can attest to you, we have a data science major at Berkeley now where we teach thousands of students every semester. It fills the university concert hall, the data science lectures, every semester. And we have thousands of majors graduating now every year. So there really are a lot of junior data scientists who know things like how to use Python and NLTK to do machine learning and data analysis on simple data sets. Okay, so we actually have many more data scientists than you need. And again, Vicky held a poll on Twitter to ask if your job title is data scientist, and this was in 2019, so not too long ago, I spend most of my time doing what? And the answer was large majority cleaning and moving data. Once again, the wrangling, if you will, of the data. And then this is last year's DICE job report. If you see, the tech occupation that actually is the hottest is not data science anymore, it's data engineering. So we're seeing this shift. The labor pool is shifting, where what we really need are people who can do the data engineering. We're beginning to have less pressure on finding data scientists. The pressure is still there. It's a wonderful profession with tons of opportunity, but it is not the high pole in the tent, as we like to say in the States. Okay, so we might have thought some years ago, if we were giving a talk at a conference like this, that the transformation in data engineering is some kind of rocket ship goal. It's a moonshot for data science. But I think this is the wrong way to think of the problem. I think a much better way to think about the problem is we need a productivity revolution for the people. We need to get the experienced data scientists tools so they can spend less time doing the data engineering, and we have to empower a new generation of people to do data engineering, because that's actually where most of the work is. So when we think about modern data engineering, there's all these tasks. There's connecting data sources, there's structuring the data, there's cleaning the data, enriching it with multiple data sets, validating that things are as you want them to be, and then deploying to production in an ongoing data pipeline, right? And all of these things are connecting from a wide variety of data sources to a wide variety of use cases for data technologies, everything from cloud data warehousing to AI to reporting and analytics. And we have these constituencies or these personas of users that have different skill sets, whether it's business analysts or data engineers or data scientists. People with these different titles today are being asked to do all this work. And so what we want to build is an inclusive environment where all of these different kind of skill sets can come together to solve problems of data science and data engineering at once. And again, to overemphasize, I'll use this acronym C. Simplicity empowers everyone. It empowers all of these kinds of workers, and we want to give them tools and technologies to simplify their work. So there's three vectors I like to talk about for simplifying the work of data engineering. The first is simply the use of the modern cloud, a place where you don't have to worry about ops because you're using platform as a service and you have auto-scaling infrastructure. It scales up when you need it. It scales down when you don't have to pay for it. So that pay-as-you-go scalability removes the need to have ops people in the loop when you want to get your work done. IT is no longer a gatekeeper of productivity. And you don't have artificial walls between teams where, for example, you have one group whose expertise makes them the gatekeeper for a certain body of data. Like, only the people who know SAS can do this work, or only the people who know Hadoop can do that work. We don't have that in the cloud anymore. There's a variety of tools and technologies that can connect to the same data sources. So cloud really removes one of the key traditional barriers between groups of expertise, the walls, if you will, between teams. A nice way to think about it, the cloud has no walls. Okay. A second more technological advance that's leading to simplification is the use of AI in machine learning in the tools that we use. We data people, we data scientists, analysts, the tools that we use for analyzing data are now imbued with AI and machine learning technologies, typically in a way that enhances our intelligence. So it's human in the loop types of AI. It's not unattended AI. And so you have interfaces where you interact with the data. The AI guides you to efficient solutions and ones that are likely to be useful to you. But you, the data analyst, the data scientist who understand the data and the domain, you get to decide what actually happens. So this is not pure automation technology AI. This is AI that helps you, the data scientist, do your job faster and better. So it's these sort of guided design interfaces. And we'll see examples of this shortly. And part of that is to have the AI not be taking on end-to-end tasks, but instead to have the AI speeding you along your work in smaller tasks. So the AI should be there in a place where you can say, yes, that's correct, or no, that's not. So it has to be relatively explainable. And the decisions it's making should be sort of bite-sized. They should be only large enough that you can validate that step by step they're doing what you want. And the key technology that I'm going to talk about in this space is what's called program synthesis, which is the computer science of auto-generating code, sometimes called software 2.0. So models and algorithms are generating some of the code for you. And this is part of what people sometimes call no-code interfaces, is the use of program synthesis to generate code on your behalf so you don't have to write every line by hand. Final piece of technology that's matured enormously in the last 10 to 20 years is visual interaction. Not just visualization of data, but the ability to directly manipulate the data visually and get the effects that you would have otherwise had to get programmatically. So you're literally seeing your data with your eyes at all times and interacting with it. And then the AI machine learning assist is translating your interactions, your no-code interactions, into code. And you can connect that no-code experience with other people who know how to write code, who bring their own code. So I like to talk about, you want no code plus your code. You want the ability for that collaboration between people who don't want to write code and people who are experts in writing code, and have them be able to work together seamlessly and respectfully, right? And that's part of an inclusive environment where you get everybody on your team working without walls. So we're going to see these three vectors of simplification in a concrete example. And what I'm going to talk about is research that began on campus at Berkeley and Stanford. The screenshot up above on the left is called Data Wrangler. This was an open source project. It's actually still live at Stanford that we built some years ago and wrote research papers about. And then in the upper right is Trifacta, which is the commercialization of that technology that my research collaborators and I co-founded some years ago. And Trifacta is also available as products like Google Cloud Data Prep by Trifacta. So if you go to Google Cloud, the data prep tool there is Trifacta. And I will say that other vendors are beginning to copy our interfaces and some of the ideas. So this is something of a trend in the industry, and you'll be seeing more interfaces with these capabilities, I think, over the next 5 years. So without further ado, I'd like to ask the folks who are operating things to play the first video so we can see this technology in action.
Today, we'll be preparing data for a credit risk analysis. We'll be using two data sets: information about the individuals we'll be issuing loans to, as well as information about the loans themselves. To get started, we've loaded a Databricks table into the Trifacta transformer view. Here we can see the raw data itself, as well as a visual profile at the top of each column. Trifacta automatically detects data types and uses that information to provide an appropriate visual summary. For instance, here we can see the distribution of values in each column, as well as a data quality summary. Here we see that a number of values are missing. As we scroll left to right, we see a quick snapshot of our data, as well as any potential issues that we might need to address. In the phone number column, we can see that there's a number of invalid phone numbers. Selecting the column gives us more details here on the right. For instance, we can see that Trifacta's pattern profiler has actually identified two different types of formats inside of our phone numbers. So let's get started with our first transformation by standardizing this column. Now, instead of writing code to clean up this data, we're instead going to use Trifacta's transformation by example. We can simply provide examples of what we want the output data to look like. As soon as we give an example, Trifacta automatically suggests a transformation to apply to the data and shows what the output will look like. Here we can see most of the data looks good, except for a few examples, which we can go in and update. When we provide another example, the underlying transformation suggestions update, and all of our data now looks good. Let's name this new column and add this transformation step to our recipe. A recipe will include all of the transformations that we add to our data, and we'll talk more about what you can do with the recipes in a bit. But next, let's add some more transformation steps. Here we can see that the credit agency is actually embedded in another string. Instead of writing regular expressions or other parsing logic to pull this data out, we can simply select the data we care about. As we interact with our data, Trifacta suggests potential transformations to apply to it. We can scroll through these suggestions and see some quick previews, as well as look in the grid for visual preview. Let's provide another example. In Trifacta, suggestions will update. Once the data looks good, we can add this step to our recipe. Next, let's standardize these titles. We'll begin by formatting it so all of the titles are in the same case. And then use Trifacta's standardization tool to identify any potential misspellings or potential duplicates in the data. The standardization tool will automatically group values that look similar. Since these clusters look good, we'll use our auto standardize feature to automatically map each value in the cluster to the most common value. And again, we'll add this step to our recipe. Now that we've added a bunch of transformation steps, let's talk about the recipe itself. The recipe serves as an interactive history. You can go back through each of these steps in the recipe to see the data at that point in time. For instance, if we go all the way back to the beginning, you'll see the raw data before we apply any transformations. We can also select any steps in the recipe to perform a number of operations. We can disable or enable steps, copy and paste them, move them around, or even combine them into reusable macros that we can share with others on our team. Additionally, we can parameterize these steps of the recipe for more operational use cases. But for now, let's add some data quality rules to ensure that the data we produce conforms to any expectations we might have. To add data quality rules, we can either add them manually or use Trifacta's adaptive data quality, where we will automatically suggest rules based on the data itself. Let's view the suggestions. Here we see Trifacta provides a number of suggestions, such as the member ID must be a valid integer, as well as be unique across all records in our data set. Let's add a few rules. And once we add these rules, we get a quick summary of the data quality at this moment in time, and we'll also be able to apply these rules later as new data comes in. Now that we've cleaned up this first data set, let's join it with the other information. We'll select another Databricks table, in this case, the information about the loans themselves. Trifacta automatically suggests a potential join key to combine these data sets. We'll then select the columns we care about. In this case, we'll include all of them except for the redundant member ID column. And we'll add this join to our recipe. Now that we've combined these two data sets, we're ready to publish this out to another Databricks table. To do so, we're going to run a job on Databricks leveraging Spark. By default, we've configured to publish this data to a new table each time. Let's take a look at some of the other settings. Here we can see we have options to publish this data as a Delta table or as an external table, as well as some other options. But for now, let's keep the default settings. And run the job to publish the output. While this job is running, let's look at some other features of Trifacta. The flow view in Trifacta provides a high-level summary of the data sets that you're working with, the transformations you built, as well as the output that you're producing. Here we can see the input data sets that we joined together, the recipe we created earlier, as well as the output that we're producing. We can also add notes and annotations to describe our work. The flow view is also very interactive, so you can add recipes or reorganize the flow. We can add data sets to this flow view if we want to augment our analysis with any other data. We could load additional data from Databricks or from any other number of connections, including applications, databases, and file systems. We can also share our flows with other team members, set up a schedule to run these flows on a recurring basis, or set up notifications or configure this to run with other third-party services. For more advanced orchestration use cases, we can use Trifacta's plans. Plans can be used to orchestrate tasks within Trifacta as well as tasks outside of Trifacta. For instance, here, we've built another flow to handle any failure cases with the flow that we just built. And we've also added a call out to a third-party service to process any high-risk loans. Now, let's return back to the flow we built and check out the output that we've created. On the job results page, we can see a summary of the job that just ran, as well as more detail about the data that was produced. On the profile page, we see details about each column, including the distribution of values, as well as a similar data quality bar that we saw earlier. And the rules page shows a summary of the data quality rules that we created earlier, ensuring that our data is high quality for any downstream analysis.
Okay, I believe that was the end of the first video. Thank you very much. Hopefully that gave you a flavor of how some of those technologies of cloud, of AI machine learning, of visual interaction can be brought together to allow experts to go much faster doing the work of data preparation and data engineering, and to allow non-experts to be able to use no-code interfaces to do a lot of this work on their own. This past April at the annual Trifacta Conference Wrangle Summit, which we ran with Google Cloud, we also announced our support for Trifacta being able to auto-generate code in Python, pandas, so that you can download your recipes into your Jupyter notebooks, into your Python programs as pandas, but use the Trifacta interfaces to speed you along the way in authoring that pandas code. And we also announced the availability shortly of the ability to generate SQL and DBT scripts, if you're familiar with that standard. It's an open source tool for orchestrating SQL scripts. So I want to show you one more example of how people who like to work in a coding environment like a Jupyter notebook writing Python can get the benefits of the Trifacta style of technologies as accelerators to their work. So this is no code meets your code. And to do that, let's look at the second video. We're going to see Jupyter, Python, and pandas working together with Trifacta. Please play the second. So to begin, we import the pandas and Trifacta Python libraries into our Jupyter notebook, and then we're ready to move back and forth between Python code and Trifacta's AI-assisted visual interface. Next, let's load up the member info data that we looked at previously, but this time instead of getting it from Databricks, we'll take it from a CSV file on our desktop. And here we can see the data frame that contains that data, and we'll have a careful look at that rightmost column as we go. Now our next task is to pass that Python data frame to Trifacta. To do that, we'll use Trifacta's Wrangle API, which is going to give us back a Wrangle flow object. We'll call it WF. In the back end, Trifacta is creating a full-featured wrangling flow that we'll be able to look at later in the Trifacta user interface. To see the data in that Trifacta Transformer UI, we just invoke wf.open, which pops open a new tab for us to work in. And when we're done with that tab, we can return here and continue coding. So here in the Trifacta transformer interface, we can look at our data, scroll all the way to the right to look at that field that we wanted to extract the suffix from. And we can use Trifacta's visual interaction by giving one example, and then a second example, and by that time, the AI can recommend the right recipe step for us. Keep an eye on this recipe because we're going to be translating it to Python. Moving back to the notebook, there's a bunch of facilities that we can access through APIs to generate outputs, data profiles, and other information from our flow. To start with, let's fetch all the profiling metadata from Trifacta in a programmatic form as a single JSON object. This is useful if we wanted to write Python code that works with the profiling information. Now, as you can see, what we get back is a pretty large JSON object with a lot of detail in it. And in many cases, what we actually just want to see is a visual overview of the profile. So we can pop back into Trifacta with a simple API call and see Trifacta's visual profile. And as we scroll through the columns, we can look to the right and we can see that new column that we generated in its full distribution. Returning to the notebook, we also might want to get the data out of Trifacta's run as a data frame in Python. So there's a simple API to do that, which is just wf.output. And here we're back in our familiar Python data frame. And again, this is the data at the end of the run. So if we look at our rightmost column, there it is, having reflected the transformations done in Trifacta. Now, in some cases, we don't want the data from the Trifacta flow. We actually want the logic of the flow converted into a form that we can integrate with the rest of our code. So in the Python ecosystem, what we'd like to get is Python code using the pandas library. Trifacta's backend can auto-generate that pandas code for us with a simple API call, getPandas, and even populate our Jupyter notebook with the result. If we were in an SQL and DBT interface, then what we would see here is a DBT YAML file that was pointing to a set of generated SQL files. Once we have this resulting pandas code in Python, we can test it out on our original dataset df. So here we're strictly running pandas code on a data frame. It's just that pandas code was auto-generated from our visual interactions with AI Assist in Trifacta's data engineering cloud. And that Python that we've generated is suitable for checking into Git or emailing to a friend or posting. Well, we got about 90% of the video. I guess the last thought there is that one of the advantages of translating things into code is that it's easy to share as a textual object. So there's lots of sharing facilities within tools like Trifacta, but there's sometimes no substitute for the ability to turn code into text. Then you can put the text on Stack Overflow, you can put the text in Slack to your friend, and so on. You can version it in Git. And so that's part of the advantage sometimes of translating recipes built with no code into code that you can manage like you'd manage any code asset. So we'll move along. Hopefully you got a sense of how technologies that we originally developed on campus and then have translated to practice in Trifacta and Google Cloud Data Prep, how these kinds of technologies allow us to have incredible simplification of the data engineering lifecycle. No ops people to set up machines and manage them because of the cloud. Lots of assistance along the way from AI and machine learning to help guide us to good steps in our recipes. And then visual interaction at all times so you're constantly seeing your data and translating no code to code that can interact with your code. All right, I want to close on an organizational note. So a lot of talk about the tech we invented on campus, who it's for. Bottom line is that data engineering cloud should be for what I like to call T-shaped teams. Now, you may have heard of the notion of T-shaped people. These are people who have depth in a certain application area. Like you may be an expert in the banking industry, but a good data scientist, or sort of an idealized data scientist, has depth in a field like finance or high energy physics or whatever the field is you're applying the data science to. And then breadth in the ability to pick up computer science and statistical technologies and apply them to the field. So this was, originally the goal in data science was we need to build these T-shaped people. But a much more natural thing that happens in larger organizations is to build T-shaped teams where different constituents on the team have different forms of expertise. Maybe you're an you're an expert in the domain, like in a business. Maybe you're an expert in the plumbing of these tools, like in engineering. Maybe you're an expert in the analytics or the machine learning. And these teams need to be able to work together in an environment that doesn't have walls between them. And so T-shaped organizations are really what we should be inspiring to empower with technology. So as I say, simplicity of the technology empowers everyone all across these teams, and it empowers them to collaborate by allowing different user experiences and different skill sets to interact on the same data and the same generated software and operational infrastructure. So to take some takeaways from this talk, T could also be for takeaways. My first piece of advice to working data scientists as well as to students is to get out of your code and get your eyes on your data, and to do it almost at every step if you possibly can. And so interfaces like Trifacta do that for you. They're constantly showing you a visualization of the state of your data as you work it. It's like clay on the potter's wheel. You're not only shaping it, but you're seeing what you're getting, and you're interacting with that shape as you make it what you need. And too often in our classes and too often in our tools, like Jupyter Notebooks are a great example, it's a lot of work to get a visualization at every line of code, right? You have to write a piece of visualization code to see what your code is doing to your data, which is a shame. Data engineering is not software engineering. It is not a code-centric exercise, it's a data-centric exercise. So do whatever you can, pick the tools that suit you, but get your eyes on the data all the way through your life cycle. It's incredibly helpful. The second is, of course, we want to use the latest algorithms in AI to assist us in our work. There's no reason we have to do all of this stuff by hand, typing every line of code interactively. Writing regular expressions brings almost nobody joy, right? As a concrete example. Writing Panda scripts doesn't bring too many people joy either. So let's use algorithms in AI, but we do want to use them in their place. We want to make sure that the people responsible for these data pipelines and these outputs can attest to the correctness of these pipelines and these outputs, because they lived through all the steps. Even if they didn't write every line of code, some of the lines of code may have been generated by software. They know what those lines of code are doing, right? They know what the inputs look like, they know what the outputs look like, and they know roughly what the step was that went from input to output, yeah? And so you want to get this interaction between human intelligence and artificial intelligence, and that requires you to have human in the loop style uses of algorithms in AI. Here's an infamous example of AI gone wrong in data transformation, right? You may have seen this. This is actually what you get out of Excel's flash fill if you're sort of just type Jan and do January. And of course, this is not the algorithm's fault. The algorithm is a heuristic. AI, by definition, is the science of heuristics, okay? But you need human interaction with the AI, particularly in the fussy field of data preparation, data cleaning, data transformation. You really need users in the loop examining the data as you go, even when you're using these technologies, or especially when you're using these technologies. And then finally, code synthesis is an incredibly powerful new tool in our toolbox of computer science that can allow what used to be aspirationally no code, which was really just kind of drag and drop stuff that did very simple things, to really generate code now. It can really take the burden of authoring code off of the end user, both for experts and for non-experts. But you want to make sure that your no-code environment and your coding environment can be integrated. And so not just program synthesis technology, but the way it interacts with visualization and the way it interacts with coders. Okay, all very important. All right, well, that's mostly what I had for folks today. Transformation through data engineering and data science is key to, I think, all the organizations we're interested in working with. And the transformation of data is the heart of that pipeline. Getting from your raw data to the data that you're ready to run your models and your analytic algorithms on, that is data engineering. It's the pipeline of data movement and transformation. The meaty stuff is in the T. T is also, of course, for Trifacta. I hope you'll try out the software. It's free online. You can try Google Cloud Data Prep. You can try Trifacta, cloud.trifacta.com. Check it out. Thank you very much.
Thank you very much, Joe, for the inspiring talk. Right on time, we have just 1 minute left for towards the end of the presentation. Do we have any questions from audience here or the virtual audience present at home? So I will have one question, actually. There are Oh, there is one from the audience. Will there be such an interface for Apache HOP or Apache Airflow in the future?
Interesting. So Airflow, as a workflow tool, can call out to Trifacta. Trifacta's own, what we call plans, which you saw in the video, don't actually make use of Airflow. They make use of Activity, which is an alternative workflow engine under the covers. And so it depends on whether you're trying to orchestrate your Trifacta recipes or whether you're trying to build an interface for Airflow. We don't offer an interface for Airflow, although there's a company, as you probably know, in the Airflow space that a friend of mine, Scott Yara, is the CEO of, and they have a product you might be interested in.
Thank you very much. Now we have another 2 more questions, but probably we can take one because of the time constraint. Do you have an interface to MongoDB?
So MongoDB is one of the sources that we can connect to, and then bringing that JSON into the Trifacta interface is fairly clean. So Trifacta does quite well with JSON-L in particular, sort of line-by-line JSON of the sort that MongoDB works with.
Perhaps we can take the last question as well. What parts of your tool are actually open source?
So Trifacta is not an open source solution, and that's a longer conversation. As you know, at UC Berkeley, we're big fans of open source, going back to BSD Unix in the 70s and the Ingress project that kicked off relational databases. And then most recently, tools like Spark and Ray that my colleagues have built in the RISE lab where I'm a co-director. In the case of Trifacta, we chose to build it in closed source. And the short version of why is that most open source that's successful is for developers, because there's a virtuous feedback cycle. The people writing the code know the user, because the user is them. They are developers. And then contributors to the code come from the user base, because it's software for developers. When we started Trifacta, part of the goal was to be building software that's not for developers and building this really rich user experience. And our feeling at the beginning was the more efficient way to do that was actually in closed source. And you'll see that very visual tools are rarely open source. And there's a lot more to the mechanics of launching an open source business versus a closed source business that we could talk about another time. But the choice of how to build Trifacta was to build the core of the product closed source. Now, of course, like everyone else, we enjoy some of the benefits of Node.js toolkits and so on. But the actual product itself is mostly closed source.
Do we have any other questions? Thank you very much, Joe, again for joining us and giving this inspiring talk. All the best with Trifacta, and I hope that it reaches everyone in the industry. Thank you very much.
Thanks for having me.